Hello, my name is Dr. Prasad Puthiyillam. It's a continuation class of my class series on Visheshwara Technical University, Engineering Chemistry, 21CHE12 the first semester as well as second semester. Engineering Materials, that is module 2, module 3 of Engineering Chemistry, that is Engineering Materials. This class series I'm explaining about conducting polymers as well as biodegradable polymers. So the content of this particular class video covers conducting polymers introduction, synthesis of polyaniline, mechanism of conduction in polyaniline, factors influencing conducting of organic polymers. Then under biodegradable polymers, this introduction, requirements to be called as biodegradable polymers, synthesis and properties of polylactic acid. So this class series is on my YouTube channel, My Intuition. Please do like the videos and share the video to maximum, and subscribe the video and support. So conducting polymers, they are organic polymers which conduct electricity. Usually we say that polymers will not conduct, but there are certain polymers recently, not so recently, synthesized, prepared by man-made polymers which can conduct electricity. Such compounds may have metallic conductivity or can be treated as semiconductors. Generally, we say polymers as an insulator. They will not conduct electricity because of the intrinsic property called the carbon-carbon covalent bond. Because most of the polymers, they have the backbone with the carbon-carbon covalent bond. Through the covalent bond, they are the mutual sharing of electrons, where there is no extra electron, there is no vacancy for electron to travel through. Therefore, they will not conduct electricity in general cases. Therefore, the primary requirement for a polymer to be conductive is that it must have a conjugation in chain backbone for easy movement of the charge carriers. Conjugation in the sense, if there are alternate single and double bonds present, continuously a single bond, a double bond, a single bond, a double bond, that we call as conjugation in the backbone. Then the double bonds formed, the single bond as well as the double bond which is in which the one of the bond we call it as pi bond also. That is actually done or because of the sidewise overlapping of the p orbital, which is comparatively a weak bond. Therefore, it can be broken and we can make access, we can make the electrons to move through that p orbital. That I'll demonstrate, I'll show in my video class. So let me take conjugation. So the conjugation, I represent that single and double bond. I'm not giving the hydrogen there. I'm not satisfying the vacancy of carbon here. Just showing the conjugation, that is single double bonds. Alternate single and double bond. That is single bond carbon, a double bond, a carbon, again single bond carbon, a double bond to carbon. So how we can represent this double bond? This double bond we can represent, same thing I'm drawing here. Okay, I want to represent the formation of double bond. Okay, there is a vacant p orbital in this particular carbon, for this particular carbon. For all carbon atom, there are p orbital, not vacant, p orbital with one electron each. So that electron I am representing with that red dot. Now, how the double bond is formed? Why this sidewise overlapping? So this electron, it can be on this loop as well as this loop. So they can sidewise overlap. When they sidewise overlap, it forms a extra bond here, which we call as the double bond or pi bond. Okay, like that, a pi bond is formed on the given sides. Okay, here double bond is there. This side also double bond is there. Here also double bond. Here also double bond. Now, if a p orbital, if another nearby p orbital, if it gets a positive charge or even one extra electron, one more extra electron, free electrons, then it can move through this p orbitals. That I can show. If a positive charge is formed, that means this particular carbon here or particular atom present here, it is having deficiency of electron. Therefore, this pi bond will break and electrons will be given to that positive charge to neutralize that positive charge. That I am showing here. Say one electron, these two electron among this double bond, these two electron, one electron it is kept in that particular carbon, one electron given to the, therefore the positive charge there it is neutralized. So here there is no positive charge now further. That positive charge will shift here because here the electron it is moved. Okay, therefore a positive charge is formed. Now this double bond here, there is no double bond. That double bond will shift to that particular position. That means double bond is shifted, positive charge also shifted. That means electrons are moved. Movement of electrons we call it as the conduction. So here positive charge is moved in the opposite direction, electrons are moved. So this will continue. Again, one more electron from the next nearby alternate double bond, it will shift. Positive charge also will shift and the double bond formation also will shift. Now we can see earlier there was single bond here. Here it become double bond. Here double bond was there. That double bond it becomes a single bond. Here single bond it becomes a double bond. And how here is a double bond was there, it becomes a single bond now. Now here you have to get a double bond. This positive charge will shift here, the electrons will move. Okay, this is just a schematic representation to make you understand the possible shifting of the positive charge or the conduction in alternate single and or conjugation. So in conjugation like this, what I am demonstrating here, like that possible movement of a positive charge or charge movement we call it as the conduction. Now the advantages of if polymers can conduct electricity, then what are the advantages? Because polymers are lighter in weight compared to metals. The processing is easy and less energy of consumption. The processing easy means to make an using conducting polymer, any device or any related component, any component we have to prepare, its processing, making it is very easy. And the energy required for that process is also very less. They have corrosion resistance. Polymers usually they will not undergo corrosion. Metals are more prone to corrosion compared to polymers. Therefore, they have very less corrosion issues. It can be easily blended with other plastics. If a conducting polymer, it can be mixed with other plastic or polymers which have better properties. It can be blended so that the strength will be more, or other properties also will be improved along with the conducting property. Make the material compact, because polymers we know it is very easy to compress, easy to make into an device which is of lower dimension, lesser in dimension, the length or width wise. Therefore, it can be compact size material can be prepared by using conducting polymers when we compare to that of metal. Their processability mainly by dispersion. We can process the polymer, means getting converted into a device or an article. It can be easily done by dispersing in a suitable solvent. No need of high heat treatment or other complicated methods which is more energy consumption. So it can be done mainly by dispersion. That is one of the easy processability method. The electrical property, it can be fine tuned. We can fine tune, we can decide what type of conduction it is required, because we can control the molecular structure, we can alter the atoms present in the conducting polymer, we can alter the conjugation, alternate single and double bond. All those can be fine tuned based on our requirement. So these are the advantages of conducting polymers. There are some certain limitations also. The conducting polymers or the so-called organic polymers, they can offer high electrical conductivity, but do not show similar mechanical properties to other commercial available polymers. Their mechanical properties are less. They are very hard or brittle. They cannot be elongated. They will not withstand high tensile strength or impact strength. All those mechanical properties are comparatively lower in case of conducting polymers when compared even with the other polymers which are non-conducting. The strength to size ratio of polymer is less, while for metal is more. That means for the given size, if we compare a polymer, a conducting polymer and a metal of the same size, then if you compare their strength, the strength of the polymer is less compared to that of metal. It cannot be machined easily and the limited speed for machining for it. That means once we convert into a device, further changing, molding it to other shape or converting it to some other form, it is easy with metals. We can machine it, we can cut it, we can grind it. All those processing methods are easy with metals. Whereas with the polymers, conducting polymers, it is not that much easy. The heat capacity of polymer is very less, so cannot be used in heat applications. Heat capacity means the ability to absorb the heat. In high heat conditions, the conducting polymers will not work. They may melt. They will become softened, or even undergo degradation. Whereas metals usually can be used in a little bit high temperature also. Therefore, heat capacity of polymer is less. so cannot be used in heat applications. And a heavy structure cannot be made by conducting polymer. Already we said, I said that the mechanical properties of conducting polymers are less compared, even compared to the other polymers. Then important examples of conducting polymers which are available in market, which are used in market, which are used for application: polyacetylene. Polyacetylene, I'm drawing the polymer structure, only this much part, that is single bond CH, double bond CH, single bond. It will repeat n number of times. N can be any numeric value higher than that of 500 or 1000. That much high number, when it repeats, then only we call it as a polymer. Therefore, polyacetylene is an example. This is a simple schematic molecular representation of polyacetylene. Polyphenylene vinylene. Polyphenylene vinylene drawing benzene structure attached to a single bond, benzene structure. Then CH, a double bond CH, single bond, and it continues, repeats. Okay, so this particular structure, if it repeats, then we can call it as a polyphenylene vinylene. With this phenylene vinylene, the vinyl group attached to vinylene group. Okay, therefore we call it as polyphenylene vinylene. Is also alternate single and double bonds are there. In the benzene ring, alternate single and double bonds already there. Then it is connected to a single bond with CH, a double bond with CH. Then again it is connected to a benzene ring only. Okay, therefore here also alternate single and double bonds are there. Therefore it is also a conducting polymer. Polypyrrole. It is a heterocyclic compound, a heterocyclic organic compound made up of converted into polymer structure or polymer form. That means it will repeat n times. Okay, so here nitrogen is there, a lone pair which is a part of this conjugation. Then again connected to another 5-membered ring with nitrogen, which also contains alternate single and double bond. So single bond, double bond, single bond, a double bond, single bond, and a lone pair of electrons, 2 electrons, which give the same effect as that of a double bond. We know double bond is found by 2 electrons by a sidewise overlapping. That 2 electrons are there on the atom of nitrogen also. Then similarly, if sulfur is there in place of nitrogen, then it becomes polythiopin. Polythiopin is also conducting polymer. Example for conducting polymer. So repeats, this structure repeats n times. Polyaniline, one of the very important example, that is polyaniline. That is polymer made up of aniline, that is C6H5NH2. It convert into polymer form, polymeric form, that is C6H4NH, which repeats n times. That is single bond here, then benzene ring alternate single and double bonds, and single bond with the nitrogen having lone pair of electron, then a double bond. So it gives the effect of alternate single and double bonds. Polyphenylene sulphide, similar to that of polyaniline. In place of nitrogen, sulfur is present, just like pyrrole and thiopin. Polypyrrole and polythiopin. Polyaniline and polyphenylene sulphide structure looks the same. Nitrogen is replaced by sulfur, or sulfur is replaced by nitrogen with the hydrogen, NH. Okay, so polyphenylene sulphide is also an example for a conducting polymer which repeats n times. So that structure. Now polyaniline. Polyaniline we also call it as PANI, where P represents poly, ANI represents aniline. Okay, so PANI is an organic semiconductor of a semi-flexible rod polymer family. It's a semi-flexible. It has got little bit of flexibility, but not completely flexible. Therefore, we call it as semi-flexible. And the polymer obtained, it looks like a rod-like polymer. Therefore, we call it as rod-like family. Its molecular structure I am showing. Polyaniline. It's already we drawn that. But when it becomes an actual polymer, I only shown the repeating unit in the previous example. Now in polyaniline, PANI, it consists of repeating unit of this structure. That is a single bond C6H4 connected to a nitrogen with a lone pair of electron and hydrogen, connected to another C6H4, again nitrogen H. This repeats n times. Then similar to that, a structure similar to that is amine form. This is imine form. Okay, so here it is called as amine form, NH2 amine form. Here it is only N double bond, it's called as imine form. It repeats. So C6H4, lone pair of electron, double bond with benzene ring with only two bonds in the benzene ring. The other two bonds are outside that benzene ring connected to nitrogen, which repeats n times. This whole structure repeats x times. X times means that is the degree of polymerization. Degree of polymerization means it represents the number of the chain length or related to that. I'm not going in detail. Okay, so degree x represents the degree of polymerization. That means this much structure, these two structures in bracket, it repeats further x times. This structure we have to call it as polyaniline. But different forms of polyanilines are there, which is derived from based on this, whether it is oxidative form or reductive form. Based on that, we have three different polyaniline, three different types, and they have different colors also. One that is leucoemeraldine, that is C6H4NH repeats n times. That means in this particular structure, n equal to 1. So here it is 1 and m equal to 0. That means this particular structure form is not there in the leucoemeraldine. That is a fully reduced state. It is having white color or it is colorless. The second form, that is pernigranaline, that is C6H4N, which repeats n times. It is fully oxidized state in which n equal to 0, m equal to 1. Okay, so here I can write as n or m also, C6H4N m times. Okay, so because n equal to 0 already, therefore here I can write as m also. It is blue or violet colored. Okay, here n or m it just represents a number, how many times it repeats in the structure, polymeric structure. Okay, so don't get confused with this n. It can be n, it can be m, it is any numerical value in number. Then the third one, that is emeraldine, which is important one, that's why I highlight it. Emeraldine structure, that is the same structure which is represented here at the top. It is available in green or blue colored. Now, the synthesis of polyaniline, it can be synthesized. The best method to synthesize polyaniline is by the electrochemical or chemical oxidation of aniline in aqueous acidic media. Aqueous means water. The acidic media means it contains H2SO4. So sulfuric acid, acidic media means it containing acid. It can be H2SO4, HNO3. So best suitable one, that is H2SO4. So with the dilute H2SO4, it aniline undergo electrochemical or chemical oxidation using some common oxidants such as ammonium peroxide disulfide. It is NH4 twice S2O8. So I'm drawing that structure. So let me draw the structure of aniline first. So this is aniline C6H5NH2. 4 times n number of C6H5NH2 I took. To that 2n times ammonium peroxide disulfate, which is the oxidant, then undergoes oxidation reaction in which the nitrogen having HSO4. That means I took this n. Let it a continuation of start continuing from here. Okay, so yeah, 4n times numbers are there. Therefore, 1n I took. Its lone pair of electron, it is taken by the by oxidation. Therefore, nitrogen loses the lone pair of electron, so it gets a positive charge. Therefore, a counter ion HSO4 minus will sit near to that. There is no bond between. This is just a counter ion. Like that, two structures. When a lone pair is taken, it forms a double bond with the benzene ring. Then again a double bond with benzene ring to nitrogen. So two sides we get a positive charge on nitrogen. Then continuation. Then remaining structure NH CCH4NH, CCH4NH, it repeats. Okay, so 4 aniline molecules, if I take in this side, if NH, if I take this side, it will be easy to understand. N here, then HH, then it starts with nitrogen. Again, CCH5, that aniline molecule present here, aniline type molecule present here, aniline type molecule present here. Therefore, this repeats n times. Plus 3n H2SO4 plus 2n NH4 twice SO4 as the byproduct. So this is the first step in the synthesis of or we got almost the structure. Now we can undergo rearrangement. Okay, now this is the you can say as polyaniline. This particular structure we can call it as polyaniline, which will further undergo rearrangement. This is a polaron, bipolaron. We shift it to alternate the individual, the internal rearrangement takes place. But I'll show it again. Okay, so this is you can say as the simplest method or the best method to prepare polyaniline from aniline. Now the mechanism of conduction. To make a polymer conducting, even though alternate single and double bonds are there, that is not sufficient for the conduction. It has to be doped. That means we have to introduce positive or negative charge to that. It can be oxidative doping or reductive doping. In case of polyaniline conduction, we use oxidative doping as well as acidic doping. Okay, therefore, the doping of conducting polymer, it is a result of the formation of polymer salt by exposing the polymer to a dopant in solution or by electrochemical process. In case of semiconducting materials, in physics, we studied about the doping of silicon in photovoltaic cell application. In chemistry also it comes, photovoltaic cell application. There we dop the silicon with boron or phosphorus, a pentavalent impurity or a trivalent impurity. The meaning is the same here, but we are introducing the charges on that. It can be, if PS represents a polymer segment, if it is a p-type doping, then it is attached, made to react with a chemical such a way that the positive charged part become a part of that polymer chain, polymer segment. PS represents polymer segment. The positive charge become a part of the polymer segment. That means it is p-doped. Positive charge is introduced. The A minus will go ahead. Or it can be N-type doping, in which the polymer segment is attached to an atom having negative charge. Therefore, polymer segments, now the polymer segment gets a negative charge, therefore equal as N-type doping. Okay, here the PS represents a section of a polymer chain or polymer segment. Now the mechanism, the doping and conduction further. The emeraldine base, it consists of two amine nitrogens. Amine nitrogens means it is represented as NH. So two amine nitrogens are there, and also it contains imine nitrogens. Imine nitrogens, IMINE, imine nitrogen. That is single bond N, double bond to the benzene ring. We call it as the imine bond. It is a blue colored insulating form of a polyaniline. Even though alternate single and double bonds are there, it will not conduct electricity that much. Therefore, it can be transformed into a conducting form, which is called as emeraldine salt. Now, this is the particular structure that can call it as emeraldine base. It can be converted into emeraldine salt. It can be done by oxidative doping with the help of dopants like HClO4, FeCl3, ASFi, I2, iodine, NH4, BF4, SO3CF3, HCl, HNO3, H2SO4, H3PO4, or it can be done by protonic acid doping. Protonic acid doping, the protonation of imine nitrogen atom without the electron exchange, like acids like HNO3, HCl, H2SO4, which pulls out the lone pair of electron from imine nitrogen and thereby creating vacancies in the pi electron cloud. So pi electron cloud means there are alternate single and double bonds are there. That double bonds which creates a electron cloud that is near to that atoms which are having the double bonded. There is an electron cloud. We call it as the pi electron cloud. Okay, so I took the emeraldine base. So this particular structure I can represent, I can call as emeraldine base, in which CCH by NH2 is there, then a double bond nitrogen, another double bond nitrogen, and NH. So this is a base form. Okay, to that I am adding, that is called as emeraldine base. It first we have to do protonation. It has been done protonated. That means acid is added or proton H plus is added to that. So it is clearly seen this particular right side NH is not disturbed. The one where imine nitrogen is there, though it is N, it has got a lone pair of electron. Okay, so it is a single bond N, double bond is there, but N is having a lone pair of electron. That lone pair of electron is taken and to that H is added, H plus is added. So H hydrogen proton forms bond with nitrogen. That means nitrogen's that lone pair of electron, two electron, one electron it gives to H. Protonation means we are adding H plus. So here H plus is added. That means hydrogen with a vacancy of electron. We call it as proton. So when it has to form a bond with the nitrogen, then the lone pair of electron, the electron it has to give to hydrogen to form a bond. Then nitrogen loses electron, it gets a positive charge. Therefore, wherever imine nitrogen is there, it undergo protonation. That is the first step for emerald and salt first. ES1 represents emerald and salt 1. Now it the particular obtained compound we call it as bipolaron. Now bipolaron it undergoes internal rearrangement. Internal rearrangement happen. That means here the positive charge on the near on the same benzene ring. It the internal arrangement takes place such a way that the double bonds it becomes a single alternate single and double bonds with the charge. So a positive charge, a double bond is there. So now a partial positive charge, a single bond, and then double bond, single bond, double bond, single bond, nitrogen with a partial positive charge, single bond. Therefore, this is the internal arrangement that happened. That means this electron, out of these two electrons, one electron here, the double bond is there. You can see where the arrow indicates. There, a double bond means two electrons are there in the double bond. One electron gives to nitrogen. One electron will remain to the carbon, the bonded carbon of the benzene ring, which is bonded to nitrogen. Therefore, one single electron, then this double bond, it will break one electron, it will share a double bond is formed here like this. Then this double bond is broken. Therefore, here one electron, this particular corner will having one electron. Therefore, this particular double bond will break, and here it forms a double bond. When it breaks, this particular double bond breaks two electron. One electron gives to nitrogen. Therefore, this structure is formed. I am not given this particular rearrangement reaction, but I think you can understand now. You are able, you can get the point. Here, nitrogen having. I'll repeat that explanation again. Here, nitrogen having full positive charge. Therefore, but from this double bond where the arrow indicates, from the double bond that is two electrons are shared here, double bond. One electron it gives to nitrogen. Therefore, one electron will remain with the benzene ring, the carbon of the benzene ring. Then once a single electron here, then this double bond will break. Here it forms a double bond that is represented here. That means the nitrogen got a one electron, the full positive charge converted into partial positive charge, and we got a double bond here. This double bond is already broken. Here one electron will be remaining. That will combine with this shared electrons of next NH carbon nitrogen bond. So this electron will break. When this double bond breaks, one electron will go to the nitrogen. Therefore, one electron given to nitrogen, full positive charge becomes a partial positive charge, and a new double bond is formed among these two carbon atoms. Now I think it is clear to this form we call it as ES2, emeraldine salt 2, or also called as polaron. Now there is a polaron separation, or we call it as halving, 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 that is reduction by half. Okay, now here also the positive charges are on the same and nitrogen of the same benzene ring connected to the same benzene ring. Now this will separate. It will separate. It undergoes we call it as polaron separation. That is again internal rearrangement. It will separate such a way that the alternate nitrogen will get a partial positive charge. Therefore, NH, CCH4, NH with a partial positive charge, CCH4, NH without positive charge, the CCH4, NH with a partial positive charge, then CCH4 single bond, it repeats. Okay, so this is the emeraldine salt 3 form. It is a again we call it as a polaron only, but it is emeraldine salt form 3. Now this emeraldine salt form 3, that is a conducting polymer. It has got charge carriers. Charge carrier means either it is positive charge or negative charge. So here we got a positive charge. So developed charge carrier and the presence of conjugation. Now a charge carrier is there, a partial positive charge is there. which is a vacant p orbital, a vacant can be treated as a vacant p orbital, or it gives the effect of double bond, single bond, double bond, single bond, double bond, single bond. Therefore, conjugation is also there. So alternate single and double bonds are makes the emerald and salt free form to conduct electricity. Now this form can conduct electricity. I can just demonstrate how possibly the conduction is done or conduction is can be visualized. So here I took a piece of that polymer chain in which a nitrogen having a electron and a partial positive charge connected to the benzene CCH4. Now here it is alternate double and single bonds are there. Now since to neutralize a positive charge is here, a partial positive charge is around nitrogen, or this positive charge has to move, then only we can say conduction is there. How it is done? This particular double bond it will break. So I represent with a red line. That means this pi bond breaks. Homolytically, each electron will goes to its individual carbon atoms. Individual carbon atom will get one electron each. Now this one electron, it will share with this electron, it will shift there, and we will be getting double bond nature with this, because electrons it is shifted there. Now this positive charge has to shift. The positive charge is shifted to this particular car. Therefore, this pi electron, the pi bond breaks, and these electrons, I might have said a mistake here. These electrons completely, these two electrons completely shift here to neutralize the positive charge. Therefore, here we will get a positive charge. Therefore, 1, 2, 3 electrons. Okay, so 1, 2, and the electron of the nitrogen. So this 3 electrons completely forms a double bond here, and the positive charge will shift there. One electron of this one, and it shares with the positive charge. Okay, so we can visualize it. This positive charge will shift here with this electron. This electron will come here and forms a double bond with nitrogen. Therefore, we will get a structure like this. Now it can further continue. The structure it can further, the rearrangement can take place in this manner, and the process continues. And when the process continues, we can say now the positive charge shifted to this particular carbon atom, and then further the lone pair of electron of this nitrogen will shift there, and the process continues. Now we can say the positive charge from this particular nitrogen, it is shifted to the next nitrogen, then again it goes to the next nitrogen. That means through this structure, the positive charge is moving. When the positive charge is moving, we can also say that the electron also moving in the opposite direction. Movement of electrons we call it as the conduction. When electrons are moving through a structure, we call it as it is conducting the electricity. Now the factors which influence the conductivity, that is the conjugation length of the polymer chain. That is the first point. With the increase in the extent of conjugation in a given polymer, its conductivity increases. So I can just represent it. It's a very simple logic I used. Okay, so I took an example only with the carbon, single bond, carbon, double bond, single bond, double bond, single bond, single bond, single bond, single bond. So here there are no alternate single and double bond. That means no conjugation present. Whereas in this particular structure, conjugation is present to a much more extent. Now in the first case, if a positive charge is introduced, then it can move up to the carbon where it has got the alternate single and double bond. Therefore, the conduction is possible up to this particular limit. From here, we have to take the electron out, or the external circuit has to connect from here to here. Therefore, only this much length it will conduct in that first example. But in the second example, the positive charge can move till the almost the end of this structure. That means positive charge can travel this many distance. Therefore, conjugation length of the polymer chain, it will decide the conductivity of the polymer. Okay, that is the first point. It is very clear. If more conjugation present, the conjugation length is high, then the conductivity is also increases. Now the second point, that is doping level. It means how much charge carriers are introduced, or how much dopants are introduced. Charge carrier, we call it as charge carrier here. How much charge carriers are present in the given polymer chain and its frequency. Say this particular polymer chain. Okay, so it just represent as a polymer chain. Okay, it's a conducting polymer chain, and there is a dopant here, that is a positive charge introduced. To some extent, another positive charge introduced. To others, some extent, positive charge introduced. Other extent, positive charge is introduced. That means this movement of electrons will be here. Here also movement of electrons. Here also movement of electrons are possible. Therefore, the more number of positive charges introduced in the system, the faster it will move. The positive charge shift or the electron shift takes place. If you increase that dopant, means if you increase the doping level, more positive charges are introduced, more dopants are introduced, then there is a possibility of repulsion also, because they are similar charges. Positive charge, they may repel also. Therefore, generally, with increasing the doping level of the polymer, conductivity is found to increase. But after some time, it becomes saturated and start repelling each other. Now, the third point, it is the temperature. In contrast to the metals, the conductivity of conducting polymer is found to increase with increasing temperature. At some high temperature, conductivity becomes constant. That means in case of metals, we know when we increase the temperature, then the atoms present in that. Say example, if we can take example of iron itself, the conducting iron rod, in which the metal iron atoms are bound to each other, atoms are near to each other, so that the molecular orbitals are near to each other, so that electron movement is possible. We call it as the electron cloud or electron sea. The positive charge are present in a sea of electrons that you have already studied. If you increase the temperature of that metal iron, made up of iron, then the ions will start moving. It will get higher energy. It will become corresponding liquid form or gaseous form. Okay, say because melts, it melt. First case we can say, when we increase the temperature, the metal will start melting. Metal start melting means the atoms are getting separated. Therefore, the electrons cannot jump to that extent from one iron atom to the next iron atom. It cannot jump. Therefore, we can say in general, in case of metal, if you increase the temperature, the conductivity is decreasing. Whereas in case of polymers, polymers are long chain having alternate single and double bonds is present. There is no separation as such. Only one polymer chain will be separated from the another polymer chain, but a single polymer chain remains there. Therefore, electron can travel through that, and the activity is increased. If high temperature is increased, then more energy is there. Therefore, the more energy in the sense the activity of atoms increased. The breaking of the conjugation or double bonds will be easier. For that, the movement of positive charge will be easier, or for that, the movement of electrons will be easier. Therefore, I can say that in contrast to metals, conductivity of polymer is found to increase in increasing temperature. Not to high, at some high temperature, it becomes constant. Then there is no further improvement in conductivity, because the polymer chains are separated from each other. It becomes a liquid form, or then further improvement of conductivity is not seen with the increase in temperature. The fourth one, that is frequency of current. The conductivity of materials also depend upon frequency of current, because the transport mechanism of most of these materials is hopping. That means the electrons are actually hopping, just like a rabbit. They hop, jump from one side to the next side. So the electrons or the positive charge, they are actually jumping from one atom to the next atom. Therefore, more frequently, if you give current, then the hopping frequency will increase. More faster it will jump. It is not a free flow of electrons. It is jumping from one atom to the next atom. So if you increase the frequency of current, more frequently if you give current, the hopping frequency also will increase and conduction also increase. Now, biodegradable polymer, the second part of this class. It's a lengthy video. You can pause and watch later. For that, you better like this video on the YouTube channel, so that it will be there in your YouTube system, and you can watch it later. Okay, so biodegradable polymers. Biodegradable, the degradation of material, it results from the action of a microorganism, and the material are converted into water, carbon dioxide, and methane. That means, what is the process of degradation? When we say something is degraded, in case of organic cases I'm telling, if it is degraded, that means it is converted into either water or carbon monoxide or methane. That is the smaller molecules from the bigger molecule, bigger organic compound, convert into smaller one like water or carbon dioxide or methane. Then it goes to the uh, atmosphere, environment, not atmosphere, environment as such. There are several different types of degradation that can occur in environment. The degradation can be biodegradation, it can be photodegradation. Biodegradation is that is a type of microbes, mainly photodegradation, that is because of the presence of sunlight, HNU energy, degradation takes place, or due to oxidation, some oxidizing agents act on the polymer or the material to become converted into water, carbon dioxide, or methane, smaller molecules, or by hydrolysis. Hydrolysis is the attack of water molecule. Biodegradation, it is a process by which organic substances are broken down by the enzymes produced by living organisms. That mainly enzymes are used. The enzymes are a catalyst, biocatalyst. Now, classification. Biodegradable polymer can be divided into three classes. Natural polymers or natural biodegradable polymers, which are derived from plant or obtained from plant or animal resources like cellulose, starch, protein, collagen are example for natural biodegradable polymer. Biosynthetic polymers are produced by fermentation process by microorganisms like polyhydroxyalkanoate, one of the very important biodegradable polymer, polyhydroxyalkanoate, which is a biosynthesized polymer by fermentation process of microorganism. A certain synthetic polymers processing the biodegradable properties are polycaprolactam, polylactic acid. These are the synthetic biodegradable polymer, which are man-made biodegradable polymer, in which polylactic acid is very important. I'll take the synthesis and properties of polylactic acid in this class video. The requirement to become a biodegradable polymer. From the degradation studies, the following conclusion can be drawn. By trial and error method, different studies have been done on the degradation property. Then some of the points are given by the scientist or the researcher, that naturally occurring polymers are biodegradable. Whatever polymer which is obtained from nature, like starch, cellulose, these are they undergo biodegradation without any support, without any further support. They will undergo in a natural way. It will undergo biodegradation. Synthetic addition polymers with the carbon as the only atom in the backbone does not biodegrade at a molecular weight above 500. If the polymer is a synthetic polymer, okay, don't get confused with the conducting polymer. Conducting polymer class is over. Now this is biodegradable. Don't think about alternate single and double bonds and all now. Now think about only polymer which contains only carbon as the backbone. There is no other atom in the main chain. Only carbon atom is there in the main chain. That we called as only carbon as the backbone. And if the molecular weight is above 500, below 500 the molecular weight, they are smaller molecule. It is easy to take. But if it is more than that, then it becomes a coiled structure or zigzag structure, a complicated structure it forms, because long chain polymers, we cannot predict the exact shape of the polymer, how the polymer chains are arranged. Therefore, if molecular weight is above 500, they will not undergo degradation if it is an addition polymer. That means two monomers are added without any byproduct, the polymer is formed. Such type of polymers we call it as addition polymer. If an addition polymer, again two monomers are added, two means n number of two monomers are added, and it becomes only a polymer. There is no byproduct is formed. Addition reaction takes place. We call it as addition polymer. If it contains atoms other than carbon in the backbone, it may biodegrade depending upon any attached functional group. That means if it contains other than carbon, like nitrogen or sulfur, any other element is present other than carbon, then such sites are prone to degradation, because there is a change in electronegativity. If only carbon is there, electronegativity is same throughout the polymer chain. If a different atom is present, then there is a bond strength will be different from compared to the other one. Therefore, the degradation can be initiated. It depends upon the other functional group which is attached here to that. Now, synthetic condensation polymers are generally biodegradable to different extent depending upon chain coupling. Condensation polymers are formed when two monomers are undergo condensation reaction. Some molecules like water or ammonia or similar smaller molecules are removed. Then a particular polymer is formed, just like polyesters, polyamide, polyurethanes. There it has got different atoms in the backbone, and there are double bonds, triple bonds present, which makes the bond variation of bond strength, variation in the electronegativity. Then they are prone to degradation. The bonds can be broken. Degradation means finally the chain has to break in different positions. The polymer chain has to break. The covalent bond itself has to break, and then it can be converted into smaller molecule like water or carbon dioxide or methane, and like that. Therefore, in case of synthetic condensation polymers, their biodegradation are to different extent depends upon the chain coupling, what type of bonds are present in that. And now the fifth point, the biodegradation rate of condensation polymers are in the given order. Polyesters are more faster biodegradation than that of polyethylene structure. So esters, we know it consists of C double bond O, single bond O bond. This particular linkage present. This is C double bond O, single bond O. This particular bond present in the polyester, in which there is a carbon connected to a oxygen with a double bond, then connected to oxygen with a single bond. You can see the electronegativity of oxygen carbon, they are different, then a double bond present. Therefore, this bond, it is not a strong bond as such compared to carbon carbon single bond. Therefore, it is prone to degradation. It can break easily. This particular site where C double bond or single bond is there, this particular site, it can be broken easily compared to other polymers. Then polyester is more biodegradable than polyethers. Ethers are having a single bond oxygen. Then compared to polyamides, that is NHC double bond O. Then compared to polyurethanes. So the biodegradation rate of the different condensation polymers like polyester, polyether, polyamide, polyurethanes, their rate of degradation, biodegradation is given here. Now, amorphous polymers are more biodegradable than crystalline polymers. Amorphous polymers and crystalline polymer. Crystallinity means where there are more well-defined structures, similar structures. There is no change. Well-planned structure. Therefore, it is break. If something is well-planned or well-defined structures are there, it is difficult to break it. Whereas amorphous, they are scattered. The polymers are different shapes are present. Same polymer chains. Similar polymer chains in different size it is present. We have no much bond between the polymer chains. Therefore, they can be degraded easily compared to crystalline polymers. Lower molecular weight polymers undergo faster degradation compared to its high molecular weight polymers. I think I already explained this one. If it is a high molecular weight polymer, that means polymer chain length is comparatively high. Therefore, it may be in a zigzag shape, or it may be in coiled shape. It may be in wounded, any complicated shape, to which the chemical attack or the environmental attack is not possible, because the shape itself protects the polymer. They forms a coiled structure to which the degradable element cannot penetrate, or it is not easy. They are somehow, they have van der Waals forces makes them stronger when they come near to each other with the coiled structure. Whereas in case of low molecular weight polymers, such van der Waals forces are less comparatively, or it can be degraded easily. Therefore, this point is also clear. Lower molecular weight polymers undergo faster degradation compared to the high molecular weight polymers. The eighth point, hydrophilic polymers degrade faster than hydrophobic polymers. Hydrophobic means which hate water. Hydro means water. Hydrophobic polymers means they are not having polarity. There are no polar functional group. If polymer becomes hydrophilic, then there are polar separation, charge separation is there in the polymer, or partial negative and positive charge separation. That means electronegativity difference is there between two elements. Then we can call them as hydrophilic, which can form hydrogen bond with the water. Hydrophilic polymers are those polymers which can dissolve in water or which can form hydrogen bonding with water. They will undergo faster degradation compared to hydrophobic polymer. Hydrocarbon polymers are less degradable than a polymer having hydroxyl functional group or NH2 functional group or cyanide functional group. That is the meaning of that. Now continuation. However, if a polymer is water soluble, that does not necessarily mean that it is biodegradable. The biodegradation of these polymers proceeds by hydrolysis and oxidation. The presence of hydrolyzable or oxidizable linkages in the polymer chain depends. It decides whether the water-soluble polymer is degradable or not. The presence of suitable substituent also decides whether the water-soluble polymer is biodegradable or not. The correct stereo configuration, the arrangement of the polymer chain, the stereo regularity also decides whether the water-soluble polymer is degradable or not. The balance of hydrophobicity and hydrophilicity. A polymer chain always completely it cannot be hydrophilic. Carbon will be there. Carbon cannot form hydrogen bonding with water. Wherever the polar separation takes place, there only it can form hydrogen bonding with water. Therefore, the balance of hydrophobicity and hydrophilicity also decides the biodegradation. If a long chain, too much chain extend, it is hydrophilicity is there. Very small content of the polymer chain having hydrophobicity. A long chain having hydrophobicity and a small part only having hydrophilicity, then it cannot undergo degradation. Alternately, if it is present, hydrophobic chain, then connected to hydrophilic chain, then hydrophobic chain, like that. Alternately, if it is arranged, then degradation is faster. These points, the points also we have to consider when we have to decide whether the given water-soluble polymer is degradable, biodegradable or not. Now, polylactic acid, which is also called as polylactide, PLA. It is a biodegradable thermoplastic aliphatic polyester derived from renewable sources such as cornstarch or sugarcane. That means they are obtained from cornstarch or sugarcane. It is a thermoplastic polymer. It can be heat treated. Heat treatment is possible, that we call as thermoplastic. Whereas only once we can heat, then it becomes a solid mass. We call it as thermoset. Okay, so polylactic acid is a biodegradable thermoplastic aliphatic polyester. It has got ester linkages, single bond O, single bond O. That oxygen single bond is present between two carbon atoms. We call it as polyester. Lactic acid, that is CH3CHOH, it is produced by bacterial fermentation of sugarcane from the conversion of starch from corn. Synthesis, the lactide monomer is from lactic acid by condensation reaction. The high molecular weight polylactic acid is produced from the lactide monomer by ring opening polymerization using stannous octet as the catalyst. So I'm giving the chemical reaction. So lactic acid, that is CH3CH OH CO OH. So this is the lactic acid structure. This is the one of the monomer used for the preparation of polylactide. Okay, so that one only I'm rearranging, same structure only. I'm taking it in this shape. Okay, that is CS3 CHOH COOH. Okay, so we call it as CS3 CHOH COOH. That is lactic acid. So I'm taking another lactic acid structure, but I'm arranging in this fashion. Again, it is CH3 CHOH COOH only. So the same thing in another fashion I took another, because to make it and undergo ring closure to make it easy to understand. I took it as CH3CHOH in a reversible fashion. I took it. Here it is CH3CHOH COH. COH is the upper side. Here COH is towards the downside. Now, when these two reacts, only two lactide monomer to show the condensation. H2O will be removed from that side. H2O will be removed from this side. Okay, so here also ring closure takes place. Here also ring closure takes place. So it becomes 2H2O minus 2H2O. Two water molecules are condensed out. Therefore, it is a condensation reaction. So, what is the word of condensation? Water molecule is removed or condensed out. Then becomes a corresponding structure. Lactide is formed. Okay, so you can follow the same structure. Okay, same structure without that H2O, which is removed. Then we get the structure. Now it is on heating. On heating, it breaks. The ring opening takes place. First, it is ring closure. Further on heating, the ring opening reaction takes place to get the corresponding polymer structure, which is a polylactide, polylactic acid, and it repeats n time. The same similar structure, it repeats n time. OCH, CH3, C bond. It repeats n times. This much structure. The first is oxygen CH, CH3, C double bond. Here I can write it repeats n times, or you can write a long chain structure also. Okay, so here since I took two lactide monomer, I completed that reaction. So it repeats on either side, the polymer chain reaction takes place. It reacts with the next lactide, and ring opening reaction takes place, and it continues the reaction. Now the properties. There are two types of lactide, which is the intermediate of polylactic acid or polylactide. Now, depending upon the structure of that lactide, whether it is L form or D form, so here it is both CH3 and CH3 are on the same downside, IH on opposite side. Here CH3 downside, CH3 opposite side. That is stereo configuration technically. So if I count, if I unto this is a this is a carbon which is connected to 4 different covalent bonds. So we can say it gives a optical property. We call this carbon as a chiral carbon. Okay, so a chirality is there. So to chiral carbon, how to name that compound? Both are similar structures, then how to name? You have to give the priority order, the atoms or group of atom connected to the chiral carbon. So first priority goes to oxygen here. Second priority goes to the carbon containing oxygen, C double bond. Third priority goes to CH3, and hydrogen we have to keep away from the observation. That means hydrogen is away from us. Remaining 3 are near to us. Then if we see the priority order arrangement, it is the L form. Okay, Leo form. It is anti-clockwise form. Okay, therefore we call it as L-lactic acid, whereas in this the other structure it is in the reverse case. Now, depending upon the whether we are having the lactide, whether it is LL lactide or LD lactide. Okay, so you can check the remaining priority, or you can check here also. This is L form, this is also L form, therefore it is LL lactide. Here this is L form, here it is D form. Okay, therefore it is LD lactide. Okay, so polymerization of the racemic mixture. If the lactide, a racemic mixture, both are present equal volume or equal ratio, both LL lactide and LD lactates are present as an intermediate, then it leads to the synthesis of a poly-DL lactide or PDLLA, which is amorphous. And amorphous polymers are more conducting than crystalline. Therefore, it is a very good conductor. If only LL lactide is the intermediate, if LL lactide only becomes an intermediate, then the corresponding polymer is PLLA. It has a crystallinity around 37% with a glass transition temperature of 50 to 80 degrees Celsius. That means whether the polymer converts from soft glassy nature, plastic nature to rubbery nature. That temperature is about 50 degrees Celsius, and its melting temperature where it becomes liquid, that is melting temperature TM, it is up to 178 degrees Celsius. Whereas if the intermediate is only LD lactide, then means D form it is present. then it increases, it has got higher crystallinity. PDLA is having, the corresponding polymer is having higher crystallinity, therefore its biodegradation will be slower compared to PLLA. PLA is used in number of biomedical applications such as sutures, stents, dialysis media, and drug delivery devices. Sutures means that is threads which are used to stitch the wounds or after operation. What they use, that is polylactic acid. It is used in stent, dialysis media, drug delivery devices. They are mainly used. This particular polymer is used. Because of its biodegradability, it can be used in preparation of bioplastics, useful for food packaging and disposal of tableware. Since they are biodegradable, once the wounds are healed, this particular polymer, it will degrade and it will dissolve to the environment or to the body. It will come out from the system. Okay, therefore they have got a different application. Even it is used for food packaging application. Disposable tablewares are made of requirement for polylactide. So that about the uh, particular class video on conducting polymers and biodegradable polymers. Hope you understood this concept. If you understood, please do subscribe my YouTube channel, my intuition, and support me. Thank you.